next speaker is Tyrone Crisp from Radboud Universiteit Nijmegen, and he'll be speaking on parabolic induction over the p-adic integers.
Thanks very much, and thanks to the organizers for having me here. So, I'd like to mention that there are apparently two different languages that some of you speak. I'd like to say right at the beginning this talk will be in the third language, which compared to those other two is, I don't know, like baby talk, like a 2-year-old trying to learn your language. And this is, in some way, this is for a reason. This is the point of the talk. The point of the talk is to try to extract some elements of representation theory for p-adic reductive groups, or for reductive groups of local fields or finite fields, which are independent of arithmetic. Just simple combinatorial, geometric aspects of representation theory, and try to apply them to some slightly exotic setting like groups over ZP. Okay, so most of this talk will be extremely elementary, and in a way I make no apology for that. Okay, so this is joint work with Mayer and Orion. We have a couple of papers on the archive, which you can have a look at if you want to see more details. So the basic question, is this. Is there a useful notion of the functor of parabolic induction, or some functor which should be like parabolic induction in the following setting? Rep always means smooth, complex representations. Is there some useful notion of parabolic induction from smooth, complex representations of this profinite group, basically a product of GLN over p-adic integers, or some other ring of integers in a local non-Euclidean field? And so GLN and GLM viewed as a block diagonal subgroup of GLN plus M. Is there some useful notion of parabolic induction going like that? And now, of course, what's useful depends on what you want to use it for. Let me tell you something that I don't consider to be useful. You could just do the obvious thing. Just pull the representation back from this group up to, say, the upper block triangular matrices, and then do smooth induction up here. Why is that not useful? It's not useful for me because it will always produce infinite dimensional representations, whatever you start with over here, unless you start with 0 representation. Okay. In particular, an infinite dimensional representation of this profinite group is going to be far from being irreducible. So unlike the usual parabolic induction, which we're all used to, which doesn't always produce irreducible representations, but it very often does, and it always produces things that are not far from being irreducible, the functor that I just described is nothing like that. Okay. So that's a non-useful notion of parabolic induction, and by the end of the talk I will have introduced what I propose might be a useful notion of parabolic induction, but some questions remain to be settled. Okay, so why would we even want to think about this? So many beautiful groups out there, why would we torture ourselves by looking at this not particularly pleasant profinite group? So here's one possible source of motivation. So it's a theorem by Nigel Hickson and Victor Nister, and independently by Peter Schneider, about 20 years old. It says the following, so that G, curly G, be locally compact, totally disconnected topological group. Acting properly on an affine building on X. Okay, so the example that many of you will want to keep in mind is a reductive group acting on its Radboud building. In order for the action to be proper, you should use the extended building. So for GL2, you should use the tree times a line. Okay, but the point of this theorem is that it works in this generality, totally disconnected group acting properly on an affine building. Then there's an isomorphism between two homology groups. First is a kind of equivariant homology for the action of G on X. I'll say a little bit more about what that means in a minute. The second, the so-called periodic cyclic homology of the Heck algebra G, the convolution algebra of smooth, compactly supported complex value functions. And I'll say a little bit more about that in a moment. But just to somehow summarize this isomorphism in a slogan, an imprecise slogan, on the left-hand side here, this has something to do with the representations of the compact open subgroups of the group G and their combinatorics as encoded by the action on the space X. These representations of compact subgroups. This has to do with representations of the group G. So there's some definite, concrete correspondence between data related to compact subgroups and data related to representations of the group G, and that's just the kind of thing that many of you are interested in a different context. So what's this group here? Let me just give you an example. Take SL3 over a non-Archimedean local field. Then what this homology is, it's a kind of simplicial homology of a fundamental chamber in the building. Like that. But it's not simplicial homology with constant coefficients. There are varying coefficients at the different simplices, and the rule is that over a simplex, you put the complex representation ring of the isotropy group of that simplex. So the complex virtual representations of this group, which will always be a profinite group because I assume the action was proper. Okay, so here I have the representations of representation ring specified this isotropy group. Over here I put the representation ring of this isotropy group. And now when I'm taking the simplicial homology of this picture, if I want to take the boundary of something that lives on this edge, the representation here, then I induce. I didn't say it, but I assume that this action is simplicial, so that the stabilizer of this edge is contained in the stabilizer of the vertex. So I induce representations from here to here. And if I combine that induction map on the coefficients with the usual simplicial boundary, assuming I just choose some orientation, then I get a chain complex. I take the homology of that chain complex, and that's what this is. Okay? So you see, this side is all about representations of compact subgroups and how the compact subgroups fit together. Okay. Over here, this is a little bit more complicated. Again, let me just give you an example, which is, well, in a way, it's an example of this. Suppose X is a smooth, complex, affine algebraic variety. So periodic cyclic homology is something that makes sense for any algebra. So instead of talking about a Heck algebra, I want to talk about this algebra, regular functions on a smooth, complex, affine variety. Then this periodic cyclic homology is just a Tyrone homology in the algebraic sense of the variety X. Okay, so the way to think about this from the point of view of non-commutative geometry, again, this is just a slogan. This is something like the Tyrone homology of a smooth dual set of irreducible smooth representations of G. Of course, this doesn't make any sense because this is not an algebraic variety, but it's, as Bernstein showed, it's somehow close to being an algebraic variety. Okay, so this is a very general fact, which in the case of p-adic groups kind of smells like something that lots of people care about, correspondences between compact subgroups and representations of the group. And so what you might like to do is try to make this correspondence with the theory of types or the theory of compact induction of supercuspitals. You might want to make that more precise. And this is a question. Question posed by Radboud, Hickson, and Kleiman. Suppose that G is reductive group of a median local field, and suppose that X is the extended variety fielding. Okay, then we have an isomorphism like this. Now over here on the right-hand side, this periodic cyclic homology is, it commutes with direct sums. And we know that this Tech algebra has a Bernstein decomposition. It's a direct sum of Bernstein blocks. So on the right-hand side, there is a Bernstein decomposition. Okay? And therefore, on the left-hand side, there is a Bernstein decomposition. And the question is, what does that look like? Can you compute the Bernstein decomposition over here at the chain level? Okay, what would that mean to compute the Bernstein decomposition at the chain level? It would mean, if you think about, say, a nice Bernstein component, whose corresponding summand here is just Morito equivalent to functions on a torus. Okay, such things exist, as I'm sure you know. Then for each cohomology class on that torus, you know that there's going to be some homology class here corresponding to it. There's going to be some collection of virtual representations of the compact open subgroups here, which is associated to each cohomology class over here. And there's going to be a kind of uniqueness. You know, if two collections of virtual representations go to the same thing, it's because they're all induced from common subgroups. Okay, this, again, has some kind of flavor of what Monica was talking about the uniqueness of types. So this, it seems to me, is something that's worth understanding. Unfortunately, it's very hard to understand. So Radboud, Hickson, and Kleiman did some computations. Several other people have done some more computations. But I think this question is still quite far from being solved in general. It seems quite a difficult thing to do. But, well, it's worth trying to do, at least. So how might you try to do it? Well, you might try to do it the way that Harris-Chandra understood the representation theory of reductive groups, the way that Bernstein understands the representation theory of reductive groups, namely via the so-called philosophy of cusp forms. Okay, by which I mean that you should break this problem up into two separate problems. One is understanding the analog of this question just for the cuspidal components, cuspidal Bernstein components. That is almost certainly going to involve some deep arithmetic, as you all know. But then there's a second part of the philosophy of cusp forms, which is once you understand all the cuspidal bits, then you should be able to get from cuspidal data for a Levy subgroup up to induced data for G using some kind of induction. And hopefully this induction procedure is somehow easy, it's somehow geometric, it somehow has to do with the geometry of the building and some simple facts about representations of compact subgroups of periodic groups. So maybe we can get a handle on this induction step, even if the cuspidal step involves number theory, which is not my speciality. So let me be very concrete. What I mean by this have a Levy subgroup inside G, then you get two isomorphisms of this kind, one for L and one for G. Right, now, I didn't tell you exactly what this is, but one of its properties is that it's functorial in the category of modules over this algebra. Okay. What that means is that if you have a functor from modules over this algebra to modules over this algebra, which has certain properties, for example, is exact, then it's going to induce a map in periodic cyclic homology. In particular, let's say L is a Levy component of a parabolic subgroup P of G, and parabolic induction with respect to P is going to induce a map in periodic cyclic homology just by this functoriality. Okay, that's no problem. So therefore, there's a map over here, making the diagram commute. A unique map over there. Question, understand this map in as explicit a form as possible. If possible, at the chain level, at the level of this picture. Okay. Now, what would that involve? Well, we know that the building of L can be embedded into the building of G in more or less a canonical way. But now the question is, what about the coefficients? How do the coefficients for the L building, namely the representations of the maximal compact subgroups, the compact open subgroups of L, compare to the representations of the compact open subgroups of G? And now we're in this setting over here. Okay, so I hope you now understand at least how looking at this diagram encourages us to consider this problem. And why was the somehow naive answer to this question not the right one? Well, in these coefficients, we're always talking about finite dimensional virtual representations. So anything that takes finite dimensional representations and produces something infinite dimensional is not going to give us an answer, at least not in the most obvious way, to this question. Okay.
So in the construction, the choice of parabolic is not important?
Yeah, so that's a good question. It turns out that the induced map here, the level of periodic cyclic homology, doesn't depend on the choice of parabolic. And so that's a clue that whatever you do over here, at least by the time you pass to homology, ought not to depend on the choice of parabolic. That's a very good point. Anything else? Okay. Of course, there may be other reasons for considering this question. You might actually care about the representations of GL and Z. And of course, you know that every irreducible representation of GL and ZP will give you every irreducible smooth representation of GL and ZP will give you an irreducible representation of GL and Z. And more or less the converse is also true. Every irreducible representation of GL and Z will factor through some congruent subgroup, and therefore will just be a tensor product of irreducible representations of GL and ZP for different choices of prime P. Okay. There's another reason why you might study this question, but this was my notation. All right, so let me propose an answer to this question, which I'm still not sure is really a good answer, but I'll at least give you some evidence to suggest that what I'm about to write down is not completely ridiculous. Here's a general definition that G is a finite group. And I'm going to produce representations of G, smooth, complex representations of G from representations of certain subgroups. Now I'm going to tell you what kind of subgroups. So here's a definition. A virtual Iwahori decomposition. G is a triple closed subgroups of G. U, L, and B, closed subgroups of G, with the following properties. So, closed subgroups. Such that, if you know what an actual Iwahori decomposition is, you should be able to guess most of what I'm about to write down. The first property should be that the group L normalizes both the other groups. Second property, which is why the word virtual is there, the map from the Cartesian product, U times L times V into G, is given by multiplication. If I were going to write down an actual Iwahori decomposition, like of the Iwahori subgroup, I would say that this is a homeomorphism, is a bijection. I'm not going to say that, I'm just going to say that it's one-to-one. And the next point is going to imply that it has an open image. This is where virtual comes in. It's not an actual Iwahori decomposition, but it's an Iwahori decomposition of some open subset, not necessarily an open subgroup. Okay, so the third point is that there exist small, arbitrarily small, open normal subgroups of G, such that if I intersect U, L, and V with this open normal subgroup K, and then do this product, then the result is exactly K. Okay, so there exist small open normal subgroups which have an actual Iwahori decomposition in these three groups. Okay, and I'll just stress once again that the important point is that the image of this map need not be a subgroup of G. So I'll get to some examples in just a moment. First, let me tell you what the induction procedure is for such a triple. So I'm going to define a functor called IUV. So I'm in this setting here. IUV, it goes from the smooth complex representations of L to the smooth complex representations of G, and here's what it does. Suppose you start with a representation X. So I'm giving X as a vector space with an action of L. Okay, now if you just forget V for a moment, I have a pair of subgroups L and U inside G. L normalizes U, and the product from L times U into G is one-to-one. In other words, the semi-direct product of L and U is a closed subgroup of G. So I can do what I told you at the beginning would be silly to do. I can just take the representation X, the representation of L, consider it as a representation of L times U, just by letting U act trivially, and then introduce up to G. Not let myself enough space. Okay, this is not the end of the definition. Because I can do the same thing for B. And again, get something that's not the right answer. This will also be infinite dimensional in general. But between these two induced representations, infinite dimensional representations, there's a canonical intertwining operator, G intertwining operator, which just takes, if you think of this as somehow LU equivariant functions, X valued LU equivariant functions on G, take such a function and just average over the action of v. Because L normalizes v, you're going to end up in an LV equivariant x value function on G. In other words, an element of that space. And what I'm going to define, this functor is just the image of this canonical intertwining operator. Okay, and that might resonate with some of you if you've, if you know the details of this Langland's quotient construction. It's a similar idea, although not really the same flavor. This will not always produce irreducible representations like the Langland's quotient does. It's a similar idea. Okay, and I should say this: the idea of doing something like this in a slightly more restricted situation is originally, I think, due to that, which we borrowed. Okay, so there's an induction functor. There's a corresponding restriction functor. The representations of G, the representations of L, which does kind of the reverse. You take U invariants or co-invariants, it doesn't matter, these are compact groups. Take the U invariants of Y, the V invariants of Y, and project one onto the other by integrating over V. Take the unit of that. That's what I want to define as my restriction functor. So, a very simple definition, which on the face of it involves no complicated arithmetic structures, just a triple of groups satisfying these abstract axioms. We get two functors like that. So some general properties of these functors. So firstly, these two are adjoints to each other on both sides. Secondly, so I started with U and I went over to V. I could have done the other thing and I would have got an isomorphic functor. And same for the R's. This and this imply the same thing for the R. Right. Thirdly, and the key, well, at least one key property based on everything I've told you so far, is that this functor, this induction functor, does take finite dimensional representations of L to finite dimensional representations of G. Okay, that's not immediately obvious, I don't think, because we're taking the image of some intertwining operator between two manifestly infinite dimensional representations, but it turns out the image is always finite dimensional. And if you play around for a little while, it's not, that's not an extremely deep fact, but let me not prove it for you. Okay, and so as I said, that considered a slightly more restrictive case of these functors where the product ULV is a subgroup. Let me tell you some properties that established that hold if this product ULV is actually full of G, then this induction functor does preserve irreducibility. So in this sense, it has somehow the flavor of an inflation procedure rather than an induction procedure. It's a more restrictive term. And it also has the property, just like inflation, that if you inflate or reduce and then restrict, you get the identity. Okay, these two properties hold in this special case, and actually we've already accomplished. So just getting back to the question about which parabolic subgroup do you choose? this idea of somehow enforcing this isomorphism. You have an operator going this way and an operator going this way. What this definition does is enforces the independence of the choice of u versus v. And it's not immediately clear from this, but it's also true that if, well, no, let me save that comment for a little bit later, where it will be a little bit more specific. Alright, so over here we have some general properties. Now let me show you, basically the rest of the talk is going to be a bunch of examples to try to convince you that this notion is not completely useless. And by the end of the talk, I hope it will convince you. Okay, so some examples. So the first example, so I was talking about profinite groups, but of course finite groups are profinite groups. And for profinite groups, this condition on the existence of small open normal subgroups, you can ignore that because the identity subgroup will have that property. So for finite groups, these conditions become quite a bit simpler. Suppose I have a finite reductive group. Group of points of a finite reductive group. Suppose I have P, Q, an opposite pair of parabolic subgroups. Okay, well then the triple QLP is one of these virtual Iwahori decompositions of G. Okay, what do you need to check? Well, you need to have closed subgroups, that's not an issue, these are finite groups. L needs to normalize U and V, that's obvious, and the product of U times L times V into G needs to be 1-to-1. That's also obvious if you know what a parabolic subgroup is, and what a pair of opposite parabolic subgroups are. So this is one of those things. So I get a functor like that. What is that functor? Well, there's a theorem of Calvert and Lehrer, which says that in this case here, these intertwining operators are always isomorphisms. So the image of this isomorphism is the whole thing. So in this case, we just get the ordinary parabolic induction. So let me just write it like that. I, U, V is isomorphic to, let me just say I, U. IV is a circle. In the context of finite reductive groups, they're often called Parrish-Chandler functions, Parrish-Chandler induction. Okay, so in the case of finite reductive groups, this slightly complicated definition is the same as the usual definition. And that's good, because the usual definition in the case of reductive groups over finite fields is perfectly adequate. Okay, so this, I think, is a positive observation. Second example, that curly G be a reductive group over an Archimedean local field F. Let say LU, V, LU, Q, LV, again an opposite pair of parabolics. G. And let's say sigma be a face of the Brouwer-Tix building, extended Brouwer-Tix building of L. Then follows from the work of Brouwer-Tix. If I look at the triple, the subgroups that I get by intersecting the curly U, curly L, and curly V that are on the board with the isotropy group of this sigma, then what I'll get is one of these virtual Iwahori decompositions of the isotropy group of sigma in G if I embed the building of X, of L into the building of G in an appropriate way. So this is a virtual Ilhori decomposition of the isotropy group of sigma thought of as a point in the building of G. Okay, but what's the issue here? The issue, so again, this the fact that the product of U, L, and V into G is one-to-one, that's no problem. The problem is the existence of these small open normal subgroups, and that's something that Radboud has established. Okay, so again, we get induction functors. Let me just call them I sigma. And the representations of the isotropy group of sigma in L, the representations of the isotropy group of sigma in G. Okay, so this is starting to look like what we wanted for this motivation. We have, for each point in the building of L, we have at least a functor, or a map, from the representation ring of the coefficients over that simplex in the equivariant homology with respect to L, to the coefficients for the equivariant homology with respect to G. So you might hope, if you're an optimist, you might hope that these maps all assemble to give a map at the level of chain complexes whose induced map in homology is equal to this induction map in periodic cyclic homology, which I wrote down over here. And, well, in some cases your hope would be justified. So, unfortunately, in not very many cases. So, here. For SL2, and its diagonal Levy subgroup, what I just said is indeed the case. Assemble all of these maps for all of the various spaces of the building into a map of the chain complexes computing these equivariant homology groups. That is a map of chain complexes, and its induced map in homology makes this diagram commute. In this special case here. I believe this will hold, at least you do get a map of chain complexes for any minimal Levy subgroup. And I believe it to be the case, although I've not actually checked the details, that the diagram will still commute there for the case of a minimal Levy. You definitely do not get a map of chain complexes for non-minimal levies in general. But, I mean, that's perhaps not the end of the story, because after all, we're looking for a map in homology. And, I mean, there are many more ways to construct a map in homology than just writing down a map of chain complexes. So maybe this idea, the usefulness of this idea does not end with minimal Levy subgroups, but for the time being, I don't have anything to report on that. Let me now give you a concrete example, which maybe tether this notion to something that you're more familiar with. That I, so what was previously called G is now going to be called I. I is the Ilhori subgroup in SL2. O is the ring of integers in sum. F and P is the ideal, maximal ideal. Now this group has a standard Ilhori decomposition, which probably you all know. In fact, one of these Ilhori decompositions of the kind over here. So we get a functor in the representations, smooth representations of L, smooth representations of the Ilhori. What is that explicitly? Notice here that U times L times V is equal to I. So by this result of that I mentioned, this functor is going to send irreducible representations of L to irreducible representations of I. Okay, and what does it do? Well, perhaps you can guess what it does if you had some lectures on types last week. I'm sorry I wasn't here last week, so I don't know if what I'm saying is going to be patently obvious to all of you or a complete mystery, but let me just write it down anyway. So L is basically a copy of the characters of the multiplicative group O. And the hat means irreducible smooth representations. So take such a smooth character. Suppose, just for the sake of simplifying the formulas, that it's not the trivial character. And what I get by induction up to I is a certain irreducible representation of I. What is it? Well, it's this. You take induction, what I'll call I psi up to I of the representation which I will still call psi, where I psi is the open subgroup of I, where my bottom left entry has to lie in P to the C, where C is the conductor of psi, perhaps 1 plus the conductor. I'm never sure of the terminology. Anyway, it has to be the smallest ideal such that what I'm about to write down makes sense. Psi is considered as a representation of this group. Like that. Okay, I induce this guy up to I get a representation of I, it happens to be irreducible, and it happens to be a type for the Bernstein component of SL2, which is indexed by the Bernstein component for L corresponding to this character up to unramified lists. Okay, in other words, this functor sends a type for L to a type for G. And that's nice.
Assertion is that this is irreducible. And this is irreducible.
This is certainly irreducible, yes. And sorry, this is not a very sensible sentence. What I'm saying is that the result of applying this functor to this representation is this one, which is irreducible, and which, moreover, is a type for the appropriate Bernstein component. Okay, but the fact that it's irreducible already, I mean, the representations of this form are always irreducible when you're in this case here. So the fact that you get an irreducible representation, you knew that in advance from the general properties of these functors. Okay, final example, which is the one we began with, GLN. Where are we up to before? G is GLN ZT, or if you like, you can take GLN over, say, any finite commutative ring, or any profinite commutative ring, if you like. You see, in the definition of these functors I, U, and V, there was this intertwining operator that involved integrating over V. And that was fine because V is compact, so there's no convergence questions as there would be if you were talking about real reductive groups or something like this. Okay. As long as you could write down this intertwining operator, as long as you have compactness, then you can make the definition just like the one I made. Okay, so suppose we're looking at GLN of ZP, or any ring. Suppose you have a partition with n, the sum of two positive integers. Then you can form following block, triangular, and block diagonal subgroups. These will be a virtual Ilori decomposition of G. Okay, so we get induction and restriction functors, the representations of this block diagonal subgroup, which is a product of smaller GLNs, up to the representations of G, exactly the kind of thing that I began by asking for. Okay, and so now the question is this a useful notion of parabolic induction? Okay, well, we know that it sends finite dimensional representations to finite dimensional representations. So that's kind of point zero checked off the list. How else might such a thing be useful? Well, one criterion for usefulness would be that you're able to actually decompose induced representations using combinatorics, just like you can for GLN over a field. Right? There's these computations of Algebraic that for any finite reductive group, the intertwining algebra, parabolic and induced representation is some kind of Hecke algebra that's built on combinatorial data. And you might hope that such is also true here. And I don't know if it's also true here in general, but let me formulate a conjecture for which we have at least some evidence. So, suppose A plus B, C plus D are two partitions of n. By the way, you could do this for partitions into more than two numbers, but there's some transitivity of this induction procedure which says that it's enough to consider these guys. Suppose you have two different partitions of n, and you look at the composition of inducing using this functor IAB. Reducing using this functor IAB, and then restricting from GLN to GLC times GLD. So you have a functor here from representations of LAB to representations of LCD. Okay, and if this were GLN over a finite field, you would know exactly what this is. It's the sum of a double cosets in a Weil group, etc., etc. The conjecture is that exactly the same thing is true here. This is isomorphic to the direct sum over all matrices like this. Let me say like this: A1, A2, B1, B2. Sorry, let me consult my notes. I worked out exactly the nicest way to write this. I don't want to waste that effort. Direct sum over all four tuples of integers which have the following summation properties. The sum across the rows should be A and B, and the sum down the column should be C and D. And then what can we do? We can take a representation of LAB, and I want to write this out. Yes. Pardon me. Let me write what I was about to write in a clearer way. So the conjecture says that if you go from G representations of GAB, which I was previously calling LAB, yes, LAB, up to GLN, and then down to LCD, using induction and restriction, that should be the same as doing the direct sum, going from LAB down to LA1 B1 times LA2 B2 up to LCD, restricting and reducing, and the sum is over all quadruples of integers like this. Where down here, I'm viewing LAB as GLA times GLB, and restricting like this, and then in the middle I do just a permutation like this. Okay. I'm sorry, this is definitely suboptimal notation, but I hope you understand roughly what I mean. The induction and restriction should be the same as restricting, twisting by a Weil group element, inducing, adding over all elements in appropriate double coset space in the Weil group.
Do you mean to say that this is an analog of Bernstein's geometric lemma?
Yes, so it should be an analog of Bernstein's geometric lemma, which is an analog of the Mackey formula for, well, it's called Mackey formula, but in the special setting of finite reductive groups. So you wouldn't expect any of the geometric content of the geometric lemma because everything here is semi-simple. But that's what I mean to say. Yes. That's the conjecture. What would this conjecture imply? Why would this be a useful piece of information about the representations of GLN over ZP. Corollaries of the conjecture, if true, let me just say, it would give you the combinatorial content of the philosophy of cusp forms. It would mean that there's some family of cuspidal representations, the ones for which all these restriction functors vanish. It doesn't say anything about those, but it tells you how general representations of G are built up from cuspidal representations, and there are various ways you can make that precise. Let me just give you an example. It would immediately give you the analog of so-called Curtis duality, which you may be familiar with from the representation theory of finite reductive groups, and which also has an analog for representations of p-adic reductive groups, where it should be called Robert-Zelewitsky duality. Exactly the same thing would hold here in this case of GLN ZP, namely that there's a duality operation which takes a representation and sends it to an alternating sum of representations that you get by restricting and then inducing. And that would be an evolution. Okay. For example. Okay, so we have some tools that we've developed for attacking this conjecture. Let me just very briefly write down what's involved. So you can take GLN-ZP and just reduce everything 1p to get down to this finite reductive group, whose representations and parabolic induction functors we know very well. Over here you have a certain congruent subgroup, and its representations are parameterized by coadjoint orbits in a certain Lie algebra. This is, I mean, there's some definite arithmetic content here, but it's not, you know, it's not too scary. And what we've computed is that the induction and restriction functors here are compatible with applying Mackey theory or Clifford theory to this extension. So the induction and restriction functors here can be computed in terms of induction and restriction functors here, which correspond to very simple maps on coadjoint orbits, and induction and restriction functors here for subgroups of these finite reductive groups. For actual finite reductive groups, these induction and restriction functors, as I told you, are just Harris-Chandra induction. We understand them perfectly. But unfortunately, you don't always get reductive subgroups here. You get other subgroups too. So there are some challenges still to be faced in establishing this conjecture, but I'm mildly optimistic. Let me tell you one of our successes to end it. Apologies for going over time. There's hardly any finite commutative ring. It also applies to ZP. Since we're talking about smooth representations, you might as well restrict for any particular representation. You might as well divide out by a suitable congruent subgroup to get down to the finite case. Then inside GLNR, you could just look at the diagonal subgroup and the appropriate U and V of upper and lower triangular matrices. You could do induction from that diagonal subgroup up to GLN and then restrict. If the conjecture over there is to be believed, what you should get is some kind of just direct sum over the wild group in here of this guy, of all the twists of these representations, and that's exactly what you do there. This is just the sum. Say W of twisting by W. So the conjecture is indeed true if you, for example, if n is 2 and A, B, C, and D are both 1, or if you allow more general partitions, the analogous statement here is true. But that's all we worked out at the moment, and all I have time to tell you about, so that's it.
Questions?
This types that you constructed for the Iwahori for SL2, did you say it works only for SL2 or it works also in?
So I believe that perhaps people in this room have done the relevant computations to be able to verify that or not, but I'm not looked at the computations. I suspect so you'll get some, so you begin with a type for, say, the diagonal subgroup in SLN. You will get some irreducible representation of the Iwahori subgroup inside SLN. And I would strongly suspect that's a type, but I've not done the computation.
Yeah, meaning my interest was in which cases we know for sure that these representations are irreducible.
Irreducible.
Yeah.
So there's this criterion that at least a sufficient condition. If this product of subgroups is equal to the compact group you're inducing to, for example, the Iwahori subgroup, you always get irreducible representations. And this functor always sends irreducibles to irreducibles. That sometimes happens when this is not the case, but certainly in
You
this
have to
case.
choose that p to the power c carefully.
That p to the power c was somehow an artifact. It's not involved in defining this functor. The point of this writing down that example was that this construction with p to the c's is well known, I think, to people who know about such things. The point of this construction is it's a different construction which doesn't require choosing c. So in this construction of types, you start with the character psi, you say there is a c, and then you inflate up to this group IC and then induce. What these functors do by using the whole groups U and V, it essentially makes that choice for you. You don't need to know in advance that there is a C, you don't need to choose the C, it just happens automatically. You automatically get an irreducible representation just by taking the image of this intertwining operator. I'm not sure that's answering your question.
Any further questions?
Yes. So this, assuming your conjecture, so you define this Cartesian duality, does it sound irreducible to reproducible representation?
It should.
It should. I think it should. No?
Yeah, because it's going to be the antipode in the Zelinsky Hopf algebra that you attach to this thing. And that antipode, just by the positivity and self-adjointness of this Hopf algebra, should be asymmetric, so it should send a reducible.
Yes. And if you apply this functor, this duality to the trivial representation, so you should get analog of the standard representation.
What you will get is actually exactly the standard representation, because I should also mention this.
So what
If
is
you
the
take the trivial representation here, okay,
Yes.
then you have a way of taking representations of GLN over a field and getting representations here. As I said, our functors are somehow compatible with doing Clifford theory to this. In particular, if you have a representation, say, of the diagonal subgroup over here, and you induce, and then inflate, that's the same as if you inflated and then induced. So
it's a standard representation, an analog of standard representation for GLN over ZP.
it's exactly the standard representation to GLN of Z modulo P pulled back to GLN ZP. So this induction procedure somehow preserves the level. So if you're at level 0, then you're always going to stay at level 0.
Yes.
So the standard representation here is the standard representation here pulled back to GLN ZP.
And is this some relation with the definition of the standard representation by Peter Campbell for GLN over ZP, which I think is not irreducible?
Yeah, I'm not familiar with that.
Me neither.
Yeah, by Campbell. So I think Hill maybe made some definition also.
He also defined some induction.
I believe so.
I was
But,
wondering if some relation.
Yeah, I doubt that what I just described is the same as theirs, because like I said, it's a very simple thing. It really belongs to GLN Z mod P. It doesn't really belong up here.
Okay.
It belongs at level 0. The thing that I just described. So I doubt that it's the same as these other definitions.
Let's thank the speaker again.